Hey everybody, welcome back to another round of astronomy. Yeah, let's get going. Today, what we're going to talk about are scientific models, and maybe more specifically, rather than going through all of the models, we're just going to focus on, first of all, how do scientists do science? So, outline for you here, I have a quote. Simulations and models are just tools that scientists build in order to help us understand the universe. But real understanding is only possible when this is captured and actually challenged by actual observations. So the idea is that we build a conceptualization about how nature works, and then we have to go out and challenge that perception. We have to go out and make observations and see if they challenge how we think things actually work. Okay? So, as I've mentioned, we're going to go through and discuss several different models that appear in the historical development of astronomy. Models like the celestial sphere that we inherit from ancient Greece. And then we move forward to Ptolemy, which is like the first century Common Era. And then later on, Copernicus, a millennium later. Right at that point, right where we go from the transition between Copernicus and the next couple of figures, namely Brahe and Kepler, that's where we're going to start going from this qualitative description to more quantitative. In fact, that culminates with the ideas that Newton proposed, where his conceptualization of nature was written down as equations rather than this qualitative assessment. Okay, so here we go. Before we dive into the specifics of each of these models, we're first going to just discuss the scientific process in general. And the nature of science is kind of, I don't know, I struggle with how to really teach it, I guess, because I can give you the content, but how that content kind of connects and the skill set that scientists develop, that one I don't really have a good kind of idea on how to really quote unquote teach. Rather, I'm gonna try to lead you through the development of astronomy, and hopefully as we go through that, you kind of see where this scientific process is being applied. So what do I mean by content? Things like I can have you memorize stars and constellations, or you can sit down and think about celestial dynamics. That means how do the stars appear to move over the course of days, weeks, months. I can give you things like properties of light or physical processes, gravity, for example. And these are the content pieces that we'll see in the astronomy. But then the skill side of it, it's a bit harder for me to really define, give you a question on that. So what do I mean like that? For example, the philosophy of science, okay? Or the scientific method in general. Okay? Other things would be things like logic, moving from if I know this, then I can infer this. And if you've had a logic and reasoning class, that would be P, if P, then Q. That's kind of the setup that a philosophy or a logics class would do. Or, for example, how do we actually build models? Those are kind of skills that I'm hoping that you see as we go through the content. Okay. So let's start off with just the nature of science, the philosophy. And the question comes down to, how do we know what we know? So before you here, I have a tube. Okay? So I have a tube. And you'll notice that it has 4 knots. Okay? I've got this bottom one right here. So the question I first have for you, take a minute, pause the video. How do you think these knots are connected inside the tube? You got it? Yeah, pause the video if you don't. Okay, so, and you should draw this down. I want you to commit to an answer. Okay. So here's the next question. Okay? Based on what you drew on your piece of paper, okay, what do you think will happen if I pull on this knot? Yeah, okay, good. So hopefully you verbalized what you want. Okay? And usually it falls into two categories. Now you might have other creative ones, but generally I find that people will say one of two things. Nothing will happen. Okay, so I pull on this and nothing happens. Other people will say that it'll get longer. And I should say, what do you think will happen to this knot over here? Okay, now we go through. So you have now done an observation. You notice there's 4 knots, 1 long string. You now have a conceptualization about how you think the knots are connected, right? You drew that on your paper. That is what we would refer to as a model. Okay. Now, after that, I asked you to make, if for lack of a better word, some people will use the term prediction, some people will use the term hypothesis. What you have done is you have used your model, the thing you have drawn on the piece of paper, to guess what will happen when I pull this knot. Now, to close the loop, and where the quote that I read comes in, is that now we have to make an observation. Now we have to go through and do an experiment. For this one, the experiment is simply, let me pull on that knot. Uh-oh. And you notice what happened, right? You see that string, I pull on this knot, and all of a sudden, okay, this string gets longer, that one gets short. Now, for those of you that got that right, the model accurately described this behavior. It predicted accurately this behavior. You do not have to do anything else. For those of you whose model does not describe this behavior, you now must redraw how you think the knots are connected inside this tube. Go ahead. And this process falls into the nature of science as well. We don't like having conceptualizations that disagree with our observations. That's a useless model. Okay? If you have a model that doesn't explain the observations that you have, that is a terrible model to get altogether. Okay? Scientists don't like that at all. In fact, more often than not, we throw out that model. Okay, so now you've all got a new model on your piece of paper that describes this behavior. Okay? Now, the next question I have for you. Based on what you have on the piece of paper, what does your model say if I pull on this knot? Okay? Now, some of you will say nothing happens. Some of you will say, well, I don't know, maybe this string will get shorter. Okay? Let's go ahead. Maybe this one gets longer and this one stays long as well. All right? Okay, let's go through and do an observation. You go, aha, right? Uh-oh. You notice now, I pull on that string, I pull on this one. Huh? So for those of you whose model does not explain this behavior, you have to redraw the model. You have to scrap the old model, come up with a new one. So go. Now what do you think will happen if I pull on this one? Again, according to your model. Right? Yeah. And so now we go through and you see, oh, excuse me, I don't have a good firm hold on this. Okay, there we go. We'll go from behind. You see, okay. Right, I pull on that. I can pull on this one, it gets shorter. I can pull on that one, it gets shorter. Right? Uh-oh. Yeah. So hopefully you get an idea. I use this as a demonstration, getting an idea about building a conceptualization, doing observations, and then having to redo your conceptualizations. The most terrible thing about science, I think this is the worst part, maybe it's the best part because scientists will always be in business. The most terrible part about science is that you never get to open up the tube to see how the ropes are connected. That's also the nature of science. You only get to do the model and the exterior observations. You never actually get to look inside. Cool? Okay. I also, just to bring in a little bit of, I don't know, I guess it would be art. Okay. I always like this painting. It's L'artisan des images. Okay. And it says down here, ceci n'est pas une pipe. Okay. Translated, that's in French, it says, this is not a pipe. And l'artisan des images, that's the treachery of images. Okay? And I always like this one. I think it's a great demonstration about the difference between a conceptualization, a model, and actual reality. This is not a pipe. You say, what do you mean? Well, if we look at this, this is an image of a pipe. This is a conceptualization of a pipe. We see the image, and in your mind, you're probably thinking about a physical three-dimensional object that you stick in your mouth, you maybe pack it with tobacco, smoke it, that kind of thing. But no, that's not what this is. And Magritte put specifically on the painting to remind us of this. This is not a pipe. This is an image of a pipe. Okay? So I always kind of like that. If you're interested, I think Magritte did that one with the bowler guy with the bowler hat and the apple in front of his face, and yeah, et cetera, et cetera. Okay. So to kind of formalize this process, we've walked through this process. I'll do it as a flow chart just to be very formal about it. But the first part, the place where you start doing science, is you take any past observations and you put them together to make a conceptualization, a model, how you think those observations are connected. Okay? Like I said, when we started off, you had one observation. There are 4 knots of rope. And you had to conceptualize how you think they're connected inside. Now, after that, okay, I said, now based on what you've drawn, the model you have, you need to tell me what you think will happen when I pull on a particular rope. Okay? That's a prediction, a hypothesis. Some people use guess. I would say educated guess. And then after you have that, you've committed to a conceptualization, you've used that conceptualization to make a future prediction. After that, you have to run the experiment. You have to pull on a knot, right? You need more input. You need more information. That's what the experiment does. Okay? It gives you new information that you didn't previously have. Now, the outcome of that experiment, you've got 1 or 2 options. The first one is it agrees with what your model said. Okay? I would say it passes, right? The second option is that it disagrees with your model. The observation cannot be explained by the conceptualization that you had. And in that instance, we get a massive fail. No deer were harmed in this incident. Okay? Now the question, why does this actually make the news? Why does a deer crashing through a store window actually make the news? Yeah, aside from the fact it's interesting, I will put it in the vernacular of our scientific process, okay? It goes against our conceptualization about who visits stores, right? I mean, it doesn't have to be a scientific model, right? When we walk around, we're forming models all the time. One of them is, hey, the only things that visit stores, that visit a salon, are people. So when we get something like a 12-point buck visiting, I don't know if that's a 12-point or an 8-point. I'm not a hunter, I'm sorry, you'll have to correct me. But when we get a buck visiting a nail salon or a hair salon, that makes news because it goes against our models about who visit salons. It's a failure. And that's really where the exciting process happens. You have to take this observation and you have to reform your model. Once you've reformed your model, okay, you reform your model, You now have to go back and close the loop, make a new prediction, and then you have to keep going. The idea is as you go through those failures, as you revise your model, your conceptualization gets closer and closer to reality. It gets closer, it gets better at describing reality. Keep in mind, it's never going to be 100% accurate. There is always going to be places where our model fails, and that's where scientists really focus on to get a better and better model. It's almost like a bootstrapping process, right? Okay, now I have a comment that I would like to interject here about how scientists communicate with the wider audience. And it really comes down to this idea about models and, frankly, being a bit lazy. When you have a scientist that stands up on, I don't know, a news program and says, we know blah, okay? They're being lazy. They really mean they have a model which incorporates all of their observations and is able to make successful future predictions. Hey, we built this model based on this. We were able to predict this phenomena. We went out and observed that phenomena. We know what we're talking about. Okay? Please bear in mind, though, that really when they say we know something, they mean we have a model that gives us accurate predictions and incorporates all of our observations. Okay? That doesn't mean we know for certain or we like infallible, we are quote unquote right. Okay? There's always the possibility that somewhere later down the road, a new observation is produced which conflicts with the model. Okay? The other piece I'll point out to you is that generally the things that make the news are the failures of the model, right? We don't tend to hear very often about when the model is successful over here, when it passes. We tend to hear when the model fails because those are the times when it's really exciting. That being said, we have to bear in mind, again, it seems if you're reading the New York Times and you say, well, it seems like the only time something is published is when we don't know what's going on. Okay? When we don't know what's going on, that's the failing part. Okay? Please bear in mind that there's a lot of successes of the model that aren't getting published or that don't get widely disseminated because that's kind of, if you will, that's the boring part, right? My model is that a person's going to walk in the door. A person walked in the door. Not newsworthy, right? So there's that selection bias of what gets broadly disseminated in the sense of news broadcasts or New York Times articles, for example. Okay? The last thing I'll mention is that before you can scrap an old model, you have to have a new model that you're jumping to. Now, when we go through in the history of astronomy, the development, I'm going to basically be like, okay, well, we throw out that model and we automatically adopt this new one. Oh, nay, nay. First of all, you have to know that there's a problem with your old model, and then you have to find out the solution. You have to figure out a refinement. And that process between having a model that you know isn't correct or accurate and refining, finding a new model that is better at explaining the observations, the time between those two can be a long time, maybe a century, maybe even longer. Okay? So for example, when we're dealing with Ptolemy, I will present it as if we went from one model to the next in a blink of an eye. In reality, there could be 100 years when you're transitioning from this old model that doesn't explain all of your observations to a newer model which does. Okay? And we're always in that process. Our best model to describe gravity was produced by Albert Einstein in 1915. And since then, we have been making observations about gravity for the last century. By and large, it has held up great. But there's another branch of physics which gravity conflicts with. We can't get those two to actually mesh. And so we know that our model is not yet complete. But we don't know what the better model looks like yet. Which is why, for example, physicists keep working hard at CERN to get a better model. We just don't know what it is yet. Okay? That limbo is terrible. Okay, so I think that's all I have for you right now. I just wanted to give you a brief introduction into models. Okay, and so, keep mulling that over in your head. Think of this if that's a good demonstration. If you find yourself wanting to do this for, say, another class, say your elementary education, or if you want to, borrow that for some other larger demonstration somewhere else beyond your own personal interest, right? You want to teach others. Please let me know. I can kind of send you the instructions for this and different variations. Okay, so I'll leave it at that, but I thank you for your time. Keep up the good work. I'll see you next time.